well. They'll be fine. All right, y'all. We have 2 weeks left. Like as in 4 classes. We have very little time. So if you all look at the calendar, I'd pull up the calendar, but does it work on this? No, I can't click that thing. We have today, then this coming week, and then one more Tuesday, and that's it. Yeah. And then there's no more classes after that. Your final is on December 5th after that. That's really kind of it. So, for good or for bad, we're nearing the end, y'all. I'll let them say the joke before I continue onwards.
Okay. The joke for today is, what do you call an apology written in dots and dashes? Morse code.
There you go. So all your grades, I managed to do it. I got all the grades in. So that's exciting. Everything is updated up until yesterday from 1 p.m. Everything that you all had done up until yesterday at 1 p.m. is updated. Your clicker questions, updated. Your quiz questions, those are moved to the ones out of 4.5. Your test 2 multiple choice scores are in. All the things, so your grade as it stands is up to date. What it shows is what you have, for good or for bad. Now, there's a few so there's obviously a couple more things. We have a single quiz left. We have a single lab left. And we have the final. Those are the 3 assignments left. And then I also have to do a bunch of tweaking of the grades. Remember, there's a few things like I have to excuse a certain number of absences for everyone. That's going to be a fun task. I have to... What was the other thing? I have to calculate... No, I don't do that for this one. Eventually, when you take the final, I have to see if it will replace your lowest test grade. But all this nonsense to say, there's that Excel sheet I sent you all. You can use that at this point, plug in your final, and kind of see. You can basically at this point say, what do I need to get on the final to achieve my goals? That is where we're at. That is basically the last major assignment. So you can take all your assignments from all the various things and do that. So woohoo, exciting things. Another thing I'm probably going to do, I'll say this now. I will probably extend, so there was that quiz that was from this last week, universal gravity. I'm just expecting a lot of people forgot about it. So I'm just going to extend that till midnight tonight, and then if people miss it after that point, it'll be what it is. So if somehow, some way you all missed the gravitational quiz in center mass, I will extend that till tonight at midnight. Very, very slight extension, but easy enough to do. And then otherwise, the last thing, and I think you all can actually see this in the test scores. I don't know for sure. The average is very high on this test, like at 81%, which is, you will never see an average like that. And this is not like in any STEM class you take, that's like abnormally high. And that doesn't mean like a bad thing. Like I'm not like, oh, people cheated or any nonsense like that. No. It does mean it was probably a little too, like, I'm not how to put this? The test, I'm not aiming for a certain percentage, but, if you get to an 81, anyway, all that to say, take it as a gift. It was a fairly comparatively easy test. For an average to be an 81%, again, talk to me when you're a senior, you'll see what I mean, that when your STEM classes, when you get to later ones, 60% averages are more what you kind of see. Yeah, that sounds like you're a senior. Comp Sci. Yeah, so there you go. There's some senior Comp Sci majors tend to be able to take this class later. So you can ask him. But anywho, so I'm happy that you all did really well. There's a lot of what is really encouraging to me, because there were problems in there that I was like were sufficient difficulty. There was just quite a few that were also like kind of freebies. I won't get into details because I have some makeups, but I was really happy that there's like a good amount of like hundreds and 90s and 95s, because to do that well, that means you definitely understand it. And the free response will also give me a really good measure. That's the one I'm going to be really curious to see, the free response grades, because those were the difficulty level that I'm kind of if you can do those ones, I'm like, yeah, okay, good. You know what you're doing. They're not like crazy difficult or anything like that, but they had sufficient complexity, we'll call it. So anywho, we'll see how those look. Hopefully get those graded within 2 weeks' time. That is the goal before Thanksgiving break and everything. Yeah, that's it. I can't get any details about the test again because there's people that haven't due to a variety of makeup reasons that are valid. So I'm not going to get into any specific details. I will say my office hours for this coming week will basically be taken over by makeups. However, if you have specific questions, email me. And if you have anything you want to meet with. So starting next Tuesday, this coming Tuesday, I'll have kind of normal office hours again. But if you want to chat with me before then, just shoot me an email. We can figure something out. Any questions, comments, concerns? Okay. We are finally getting to fixed axis rotation, which I feel, I don't know if bad is the right word. I've seen on the boards people already in other classes have gotten to it. I'm like, I don't know how they did that. Maybe they didn't cover universal gravity and stuff. I don't know. Either way, there is a major thing I need to get through to prepare you all for future classes, and that's torque and moment of inertia. So basically, that's my goal. My goal is to get to that point, and there's some things I have to teach you before we get to that point, but that is kind of what I'm aiming for. I really don't know how much I'm going to be able to get through in I have 3 classes. I could teach that Tuesday of Thanksgiving week, but my plan is to make that a review day because that just seems the most reasonable. So I have 3 days to try to get through torque and moment of inertia so that for those that are going to take a statics class in the future, you know what half the content in the class, half the content in the class is torque and moment of inertia. So I got to get there. So anyway, we'll get rolling on that. And I was very confused about that. I actually moved this thing on this side. So yeah, we're going to talk about things spinning, and it's going to be a great time. Fixed axis rotational motion, which is a whole bunch of jargon strung together. Fixed means that it's not moving. Fixed axis, that's what it's going to spin around, and it's spinning. It's something that's spinning about a point that's not changing. So a wheel is spinning, and the axis is not changing. I'm not rotating it about this and then all of a sudden rotating about something else and like doing some crazy nonsense where my axis rotation is varying. The point at which it's rotating is called the axis, and that's fixed. It's not itself changing. So it sounds really fancy, but it's going to be really straightforward. The great news is everything I've taught you up to this point, basically, so all the kinematics, all the forces, even momentum, there's basically an analogous term in this. So let me just I'm going to show that to you all right now. You know what? I'm just going to even jump to that slide. We'll come back, but I want to show you all this preemptively. Where is it at? There it is. All right, so this is kind of what I'm going to prepare. Obviously, I skipped a bunch of slides to get here. Look at all the kinematics equation on the left. You've seen those. You're cool with those, hopefully. On the right, you should notice that they look very, very similar, just the variables are different symbols. Those are just the rotational variables. So instead of x, we're going to have theta. So you can see that instead of x, we have theta. Instead of v, we have omega. Instead of a, we have alpha. So this is the thing that's going to be the common thread over the next week and a half. I'm not actually having to teach you all that much new stuff. As long as you realize the stuff you've already learned, there's going to be analogies for it. So like all the kinematics equations, we just replace them with rotational variables. And they're the exact same equations. So if you're good at kinematics, if you can just it's almost like speaking another language. It's just new words for the same thing. But with the same sentence structure and all of that. So that's one example. I'm going to kind of jot this on here as well. Another one is F equals ma. Hopefully you're really familiar with F equals ma. Great news. For rotational stuff, it's torque equals I alpha. And it's the same exact logic. Torque is like force. I is like m. A is like alpha. A force makes something accelerate. A torque makes something accelerate in a circle. That's the idea. So that's the major theme I'm really going to try to convey to you all. I've mentioned this many, many times. Learning is all about connecting something new to what you've known before. That is literally how learning works. That's like, it's really, really hard to learn if you don't connect it to something you know before. Think of anything in life, if you can connect to something you have before, it's way better. And so in this case, you've learned kind of all the equations that you need for the next week and a half. I'm just going to switch the variables on you. The only exception to this, the only thing that's going to be new is calculating I. I is going to be its own little thing. All right, so we'll get to I. It's called moment of inertia. That's the one that I'm going to need to spend a decent amount of time on. Everything else, though, is stuff you've already learned. It's just a different paint job. It's just instead of moving linearly, we're going to move rotationally, but it's the same exact equations. So anyway, I'm saying that now. I really, really hope I can convince you of that. If I can convince you of that, this will be very easy for you. If I can't convince you of that, it won't be as easy for you. All right, so back to the beginning. And so just keep that in mind. The entire time I'm teaching you all stuff, I'm going to be constantly saying this variable is like this variable. And if you can understand that and you can believe me on that, life's going to be good for you. So look at that first bullet point. Relate rotational variables to translation variables in two ways. One, analogous. Two, there's literally ways to go from position to angle. Then we're going to make the relationships. Then we're going to define torque. And we're going to calculate it with the simple way. So you all remember like moment of like center of mass, there was like the easy way to calculate it with like two objects. So we'll do that with torque. And then hopefully on Tuesday, I'll be able to start teaching you all moment of inertia. And Thursday, we'll kind of finalize out with torque. I sadly might not be able to teach you all conservation of angular momentum. I may or may not. And I may not be able to teach you conservation of angular momentum. But it's the exact same stuff as conservation of energy. I just teach you a new energy term. It's the exact same thing as conservation of momentum, but it's for things spinning. So I may be able to mention it, but I might not be able to give you all. I definitely probably won't test you on it. So we'll see that as time goes on. Again, I'm going to fit in what I can, do my best job to teach you what I can. Okay, fixed axis rotation. You have an axis. It rotates about that. Fantastic. All rotational variables have tangential partners. We're going to see that again and again and again and again and again. So we'll get there when we get there. First one, and this isn't really the analogous, but it's here. I'll mention it. Arc length. Arc length is a useful thing to calculate. So this is the relationship between distance and angle. It's a really, really cool relationship. I think I may or may not have mentioned it in the past. Did I teach you all arc length before? I did. Yay. All right, great. We know it. S equals R theta. All right, we did this a while ago. So great. I'll spend 5 seconds so you can remind yourself. S is the arc length. Theta is the angle. Remember the angle is in radians. You cannot put 30 degrees in here. Otherwise it's bad. All right. Doesn't work. Has to be in radians. 2 pi radians in a circle. Fantastic. All right. See if y'all remember it. I got to open up iClicker. So get your brains working while I do that. It shall return. Piece of gum stuck to a wheel with radius 0.5 meters travels a quarter of a revolution. What distance did the gum travel? I'm going to warn you, you're going to see what's on my screen versus what's actually on the projector. It does the job, but it's not as nice. You're getting to see behind the scenes. I figured out a better way to present, so I've been doing that.
Yeah, I thought of that before.
There was two things I didn't think of. OBS, I could just change what displays capture. Yeah, I didn't think of that. And then I also wasn't certain if I could write on with this, but I can. So. Yeah. Ended up I could have done it the whole time. You know, you get better and better with these things as time goes on. All right. Give you all like 30 seconds.
It's like the first question. He said he sent it.
This is where the unit circle is your friend. It will be useful for you if you haven't realized it yet. Unit circle is very handy to have kind of on hand in your brain. All right, 10 more seconds. All right, and 5, 4, 3, 2, 1. Ka-chow. Oh, it's reminding me of things. All right, y'all did great. What's the angle? Y'all tell me. So S equals R theta. What's theta here? Pi over 2. Pi over 2. What's half of that? 0.25 times pi. And look how nice I was. I didn't even make you multiply by pi. What a generous man I am. Well, this is so unfortunate. There's a button hidden behind my highlighter. All right, whatever. We're just going to circle it. Wow. And we don't forget the units because we're not a chump. You know what we also don't forget to do? Attendance. Do. Oop. Oop. Ooh. Behold the blinky blinky.
That's why I was like, 14.
Oh, sorry, it's not on here anymore. Yeah, I
just write my name down.
Well, it does not work on those.
It's very hard to capture because the camera's kind of trash.
Oh, just go walk up to it. I should work this. I mean, it'll be a little jank, but it'll be easier. Yeah. You know, a laptop's just a giant phone, or a phone's just a small laptop. If that doesn't work, then if it doesn't work, yeah. Okay, that sounds like yeah. What's up? Oh, okay. That's fine. Yeah, I might not even do attendance in future years. This was a exercise and whether it's worth it, and I don't think it's really whether I do attendance in future semesters. I'm probably not getting a lot with it. Yeah. With the exception of labs. So I'll still, one day a week, people will still have to be here for the lab. All right, last chance. Looks Gucci. All right. Goodbye. Okay, back to teaching. All right, so first connection I want y'all to make. Theta is going to be like position. Somewhere on your mind, just kind of log that. Theta is going to be like position, all right? How do I go from position to velocity? You do derive it. That's true with respect to what? Time. Hey, look, guess what happens if you take the derivative of theta with respect to time? What do you get? Angular velocity. Wow. So there's our next connection. Angular velocity, shock and awe, is like regular velocity, but instead of measuring meters per second, it's angles per second. How many angles am I rotating every second? How many degrees am I rotating every second? So just like position. Now, what's really weird about this unit, so it's measured in angles per second. The unit that we're using for angles is radians, but radians is not technically a unit. You never put like pi radians. So to that end, radians is not actually a unit. So it kind of disappears. It doesn't actually show up. Which is very unfortunate because it's kind of hard to convey that. So the unit for this is not radians per second, but it's just 1/seconds. The radians is not really a real unit. It's not like meters. It's not like seconds. It's not newtons. It's not actually a unit. So the way we actually write this, if you wrote radians per second, that's fine. I will never penalize you for that. But it just turns out that radians isn't really a unit. You can't measure radians. It's not anywho. So this is what these two things are the same. 1/seconds. And the unit for this is called hertz, which I don't know why I didn't put that on. Well, that's for frequency, and that's where it gets funky. So we're just going to say 1/seconds to make things a little simpler. The unit for this is 1/seconds or second inverse. And again, it's because that radians just kind of disappears. And look at the bottom, y'all. Look how cool this is. What's the relationship between velocity and angular velocity? You multiply it by r. You're going to see a common trend here. So how do you go from velocity to angular velocity? Multiply angular velocity by r. Real quick, how do we go from angle to arc length? We multiplied it by r. So how do we go from angle to arc length? Multiply it by r. How do you go from angular velocity to regular velocity? Multiply it by r. Guess how we're going to go from angular velocity to angular acceleration to acceleration? We're going to multiply it by r. Isn't that nice? Isn't that a nice, consistent relationship? So easy to remember. Take your angular variable, multiply it by r, and you got your quotations linear variable. In this case, it's the velocity, linear in air quotes. Arc length obviously is not a straight line. So cool. Super, super useful relationship. If you want to know how fast an object's going, case in point, let's find out how fast that gum's going. Same gum. Piece of gum stuck to a wheel with radius 0.5 meters, travels a quarter of a revolution in 5 seconds. What is the angular velocity? So we're going to find the angular velocity, and in the next slide, I'll ask you what's the velocity. Am I doubting myself? Okay, life is good. I was worried though. If you're unsure, write it out. Remember, angular velocity is just how much did my angle change in how much time. We're assuming a constant angular velocity in this problem. That is critical. How much did my angle change over time? Just like velocity, how much did my distance change over time? What's your angle here? So what's that angle and radius? That's how much my angle changed. Pi over 2. So what was my angle again? You just told me the angle, right? So it's just pi over 2 divided by pi. It's just the angle divided by the pi. Yep. It's how much did my angle change per second. Yeah. Cool. That's the next one. What do you solve? So in this one, are you solving for velocity or angular velocity? That's that one. So it's just
So the changes.
just the angle divided by time. That's it.
Oh.
Yeah. Yeah, it's how much does my angle change? It's what's the velocity of my angle? How much does my angle change every second? Change in angle divided by change in time. Yep. All right, give y'all 10 more seconds to finalize any thoughts. This is angular velocity. How much does my angle change every second? And 3, 2, 3, 4, 3, 2, 1. All right, great. Okay. Angular velocity is this symbol. I didn't tell you all this. This is, I want to say omega. Why am I blanking on this?
Theta?
Is this theta? No,
Angular velocity?
this is omega.
Yeah, it's omega.
This is omega.
I thought you were talking about theta.
Yeah. All right. This is omega. Which, fun fact, if you ever heard the term, alpha and omega, beginning and the end. Omega is the last letter of the Greek alphabet. This is lowercase. This W is not a W. It's technically omega. It's very subtly different. I guess if you want to draw it, I just draw it as a W. But look, remember you all learned Greek in this class. Theta is a Greek letter. Omega, lowercase last letter of the Greek alphabet. It's angular velocity. It is the change in angle over the change in time. What's my angle? Pi over 2. What's my time? 5. Pi over 10. Woo! There you go. That's it, y'all. Change in angle over change in time. It is the velocity of my angle. How much does my angle change every second? But man, how fast is this gum going? Also, is this thing moving fast or slow? Before I even ask you the velocity, before you calculate it, you all just look at this problem and just think about it. Remember, it's always good to just think about what the heck's going on. Is this fast or is this slow? It's extremely slow. This thing is moving a quarter of a circle in 5 seconds. Like 1, 2, 3. Look, it's always good to just remember that these numbers mean something and you know what these mean. You know what a second is. Like, you know what a quarter of a circle is. I didn't have to teach you that before this class. So when you all answer this question about what's the velocity, you better get a small number because that's what makes sense. All right. Boom. Piece of gum stuck to a wheel, same problem, except now what is the velocity? Not what is the angular velocity. And this is where you got to be careful. The words you use matter. If you do not use precise wording, you will be confused. Velocity and angular velocity are varied by a single word. This is just velocity. Be very, very careful moving forward to make certain you're solving for the thing I'm asking for. It's very easy to mix up angular and velocity in your head considering they share the same word.
So does the iClicker thing take a screenshot of all the screens?
No, just the primary screen.
Primary?
It takes a screen, or at least it seems to take a screenshot of the screen that it exists on. Maybe that's more so. Wherever the window's on. I don't know for sure. I haven't tested it. I can't move this dock though to the other one. But now I've got subtitles, so everyone can see everything I'm saying. Yeah. It's a good accessibility feature, but it's also a little distracting. So, trade-offs, right? All right. Give y'all 20 more seconds. I'll go around and assist you. What is power? I'm gonna jump over this. What is Oh, that caught it. Alright. No, because you're not moving outside of the key to this one is velocity. Is this times R. V equals R times omega. All right, give you all 5 more seconds. 5, 4, 3, 2, 1. Pachow. All right, so, we found that omega last time was 0.1 pi. Remember, V equals omega times R. If you want to go from rotational to linear, you multiply by R. That's going to be the theme. So, V equals 0.1 pi times 0.5 equals 0.05 pi. We did it! Hoopla! Hoopla. Don't lose your pi. Don't forget about it. It matters. It's a value of 3.14. The answer between A and B is 3 times different from each other. So again, honestly, if you make a mistake on these, it's going to be something silly, very likely. So don't make a silly mistake.
Did you also do velocity over distance?
You could totally do how much distance this thing traveled and divide it by time. In fact, that's where the derivation comes from. Yeah, it's a good segue. So the question was, can't you just do distance divided by time? You can. What is the distance traveled? It's the arc length. What's the arc length? R times theta. And ta-da, we've derived the expression that I told you before. Why is velocity just R times omega? Because velocity is dx dt. How far do I move? That's the arc length. What's the arc length? R times theta. R is a constant. Pull it out. Then you've derived that velocity is R times omega. And again, foreshadowing. If V equals R times omega, how do I go from V to acceleration? What do I do to velocity to get it to acceleration? Take the derivative with respect to what? See, if you want to go from velocity to acceleration, what do? Take the derivative with respect to t. That's so weird. My d disappears. All right. Clearly that side is unacceptable. Okay, that's very odd. But look, you all get to see the oddness at least, so that makes me feel better. All right. So if we take the derivative with both sides, foreshadowing, it's still being very weird. So weird. All right, the left side of the screen is acceptable. All right, equals. All right, so what's the derivative of velocity? Acceleration. R is a constant, so you can pull it out. What's the derivative of this with respect to time? Foreshadowing. It's the angular acceleration. Ta-da! We derived the next one that we'll see in a few slides. Very straightforward. Just like, it's really, really nice. All right, don't worry. This will show up in a future slide. This is foreshadowing. There'll be a nice slide with it. So great. There's the things we've said. Summary slide. Not going to bother with it. Sure. Try it out real quick. Calculate the angular velocity of Earth. There's its radius. There is something else you need to know to solve this problem, but you can figure it out yourself. Like, I don't need to give you that because I think you all have lived enough years on this earth and days to be able to determine what you need. This one I'm going to assume you know. Yeah, anyway, there is one more thing that you're going to need to know that I did not give you, but you do know it. I know every single one of you know it. If you don't, I will be very interested in why you don't.
A lot of them are just given numbers. Given context.
Oh, fun fact, you don't need the radius of the Earth to figure this out. I don't even know why I gave it to you.
You know, good point. I did not remember.
You know what? I'm going to make your life worse. Better. Don't use that. Look at that. Just calculate the angular velocity of Earth. You have what you need in your head. Yeah, we're calculating this is a great point. It says angular velocity. There's two you could consider. You can consider around the sun. I want the angular velocity, let's say like it's spinning like a top. Okay? Around Earth's axis. That is a great point. There is two angular velocities of Earth. I want around Earth's axis. Earth is the axis, not the sun. We're going for a geocentric model here.
This doesn't.
No, that's what's cool about this. Yeah. And I'll reference that later. Tangential totally. The radius. Angular velocity. Oh, radius from the axis of rotation. Yeah. And that's, the cool connection is that's the reason you launch a rocket.
That's why we launched from Florida.
Yeah.
Okay. I was thinking from the center of the Earth, but no, it's from rotation of the axis. That makes sense.
And then because someone had a great point about its axis. All right, once you all do this, I have two problems for you. Find the velocity at the equator. Find the velocity at the pole. At the North Pole. The one that it rotates about. Yeah. This pole is the one about which it rotates. There's a cool problem that gives you a cool realization that you may not know. Let's see, we've lost the thing. Well, this is definitely what a terrible no. Okay. All right. So the answer, what was it?
7.27 times 10 to the negative 5.
All right, there's the answer to the first one. If you didn't get that, call us over. And then what's the next one?
Oh, it looked like it's like F1 over.
463. Or 464 around.
Any decimals?
I just rounded it, but it was like 463.82.
All right. So let's just go ahead and start solving this. There's the answer, so you can check it. I'm not going to give the answer to part B yet because it gives too much away. All right, so this one, I'm not going to even worry about writing the givens and all that because it's so straightforward. It is the change in angle with respect to time. What's the angle for a full circle? 2 pi. What's the time it takes for one full spinny spin? 86. How'd you get that? Did you have that memorized? No, you didn't. You might have, but probably not. How the heck do I figure out how many seconds are in one rotation? Yeah, how many hours in a day times how many minutes in an hour times how many seconds, and you get all the things. So that equals, and that was the thing I told you all that you all know. It should be a very simple calculation for you all to calculate how many seconds are in a year. Like, that's something that I don't know why that might come up in your life, but if you needed to, you all know. Okay, I say that. You might not remember 365 days in a year. May or may not. That's one of those that's like fluctuates. All right, great. The next one. The velocity disappears into the nether. I have no idea why that is. All right, great. Velocity is r times omega. Equals the radius, which is 6.378 e to the 6 times 7.27 e to the minus 5. And you get a crazy answer, which is that you all are traveling faster than the speed of sound if you're at the equator. But here's the thing. You may be like, wait, I can't be traveling faster than the speed of sound. That would mean I'd like vaporize and all that stuff. How fast is the air around you going or at the equator? The same exact velocity. If everything's going the same velocity, you can't remember, velocity is relative. Velocity is all relative. If everything around you is going the same velocity, you can't tell. If this entire building was this entire building is moving and you're moving because the earth is moving and everything's moving and so nothing changes. Now, if the earth suddenly came to a stop, then things would get really weird. If the earth suddenly stopped rotating, all of us would catapult into one of these walls. I don't know which one. Do you know which one? Oh, okay. Anyway. Would the walls not also be catapulted? The walls would, I assume the building was perfectly rigid. The building would resist, would also want to keep moving. The building would do a better job of stopping than we would because it's attached to each other and attached to the ground. But yes, the building would also top. Earthquakes, case in point, are when the earth starts to shake and everything on it's like, whoa, I'm not used to shaking, whatever. But
so are we technically like all like balancing? Like when you're on a ship and you're like that's speed, you have to like adjust yourself balance. And obviously if you stop, or the ships can slow down, you like all over. Are we all like technically balancing?
So it's not necessarily about. So the ship is more complicated because you have waves pushing the ship. So the boat is constantly changing its velocity. And in turn, you have to change your velocity to match that. The Earth is moving at a constant velocity, so you're not noticing that acceleration. You notice acceleration. Like, no matter what, you can notice acceleration. Your eyes are closed. You will notice if you're accelerating. You will get pushed in some direction. I say pushed. Everything, whatever's around you is going to move, and if it's moving and you're not, you will feel that. And yeah, so you can experience acceleration, but velocity... Once you get going to speed, like when you're in a car, outside of the noise and the vibrations, you can't tell you're going 60 miles per hour or 100 miles per hour or 30 miles per hour. Yeah.
Yeah, I was going to say, it's like when you're in a car or on
Yep.
a walkway, it's the same thing.
Yeah. A bullet train, if it's a smooth ride, you can't tell you're going over 100 miles per hour. So, great. Let's go ahead and look at the velocity of the North Pole. It's the exact same calculation. It's still, I could have put like 1 meter from the North Pole. I maybe should have put that because you can make arguments that you're not rotating. I don't know. Let's say that you're standing on the North Pole, so you are spinning in place. As weird as that sounds. You are standing right at the North Pole, so you are spinning with the Earth. You wouldn't really notice, but you are. But the case here, same thing. Velocity equals r times omega. But my r here is 0. So what is your velocity at the North Pole? It is 0. And we get a really interesting discovery here that I'll let either Angelina or Leo explain because it's really satisfying. Go for it. What is cool about this? Leo will explain. There's a real world connection for this.
Okay, so as you can see here, the farther up you are and the closer you are to the Earth's rotational axis, the less tangential velocity you do have. So you notice that we launch rockets from Florida and everything. There's a good reason because of that, because it's very south in where the U.S.'s territory is. So we have a lot of tangential velocity relative to where we are on the Earth, since we're near the equator in Florida. So rockets get a big boost from that. So it's a lot easier to get to orbit than it would be if we launched from somewhere like Alaska. And also, we have an ocean next to Florida, so if the rocket crashes down, it doesn't crash on a whole bunch of people in Montana.
So it literally saves you money. You do not need as much fuel if you launch from the equator because you literally are going faster. Like, this is not, remember, velocity is all relative, but relatively to the north of the top of the Earth, you are going faster on the equator. So if they have a really big rocket, they'll go even farther to the equator than Florida. So I think they did that with the James Webb Telescope. I think. Yes. The James Webb was launched from French Guiana. I don't know where it is, but it's closer to the equator than us. And the reason for that is it's cheaper. It's all a cost-benefit analysis. How much does it cost to ship the parts there? All that kind of stuff. Is it worth the cost and risk? And if it is, they will ship it closer to the equator to reduce the fuel cost for things that are really big payloads or whatever.
Yeah, other countries do it too.
Why does pi go away? Because we actually, pi was in the calculation.
We just multiply.
I actually plugged pi in. Yeah. So when I did the calculation here, I actually put it all in and hit enter. Yeah, that's a good question. So there you go, y'all. Now you know why they launch things from Florida, Texas, things not Maine. No one's launching any rockets from Maine. Sure, Maine's next to the ocean, but it's not as close to the equator. So, anywho, cool things, y'all. All right.
I just wanted to say that it's not only America. If you look at where Japan launches, they launch from the south of their island, closer to the equator. The USSR used to launch from Kazakhstan, I think, because it was the lowest point in their territory they could launch from. And everyone tries to launch as close to the equator as they can, and we're really fortunate because it's really big and very close. So.
Physics is not political. Like, whether you like it or not, the physics is what it is, and countries will follow that. They'll save money. If there's one thing you can trust, it's that people save money. Like, money, whether you like it or not, is a common denominator in a lot of decisions. Anywho, angular acceleration. It's acceleration, but for the angle. It's how much is my angle, the rate of change of my angle with the second derivative of time. So in this case, it's like acceleration. It's not whether you're moving. It is not whether you're moving. It's whether you're spinning faster or slower. Is your wheel spinning faster and faster and faster? If I tell you I'm going at 60 miles per hour and I ask you for the angular acceleration, it's 0. If I say I'm going at a constant 60 miles per hour, if I tell you I'm speeding up, then my wheel in turn must also be speeding up. There's a connection between acceleration and angular acceleration. So do not forget that. That is one of those things that I need you all to remember. Acceleration and velocity are not the same thing, and many, many, many people mix them up. The same is true here. This is whether a wheel is speeding up or slowing down.
So if it's spinning backwards, it's going to be negative?
That's a great question. If it's spinning backwards, so that's if it's slowing. If the angular acceleration is negative, that means it's opposite to the direction of angular velocity. And I haven't taught you all this. I've been kind of just hand-waving over this, but this is a great time to point this out. I haven't asked you all the direction. These are vectors. These are vectors, and I've kind of been ignoring that. And here's the reason I'm going to mention it now, because you raised a great point. I said if they're opposite directions, which then leaves the question of direction. If my wheel is spinning counterclockwise and you all had to give me a straight direction to tell me which way it's going, what would you tell me? Is it going up, down, left, right? Like, if you had to describe a direction, you can't say counterclockwise or, yes, counterclockwise, clockwise work, but I want something different. What would we say? And this is where you can't say up, down, left, right, can you? Like, it doesn't work. Yeah, that sounds like it's. Yeah, you could say the angle is increasing in the positive direction. But you can't say up, down, left, right. That's kind of the case in point I want to make to you all. I can't say that this thing is spinning up. Like, what is that? What the heck does spinning up mean? I can't say this thing's spinning left. So, I'm now going to foreshadow the right-hand rule. It's a very useful rule. It's completely... Someone decided this at some point. It is what it is. Why is it the right-hand rule? Probably because most people are right-handed and, there's a history behind all that nonsense. So if you're left-handed, apologies. Actually, this is probably better for you because you can write the answer while using this. Anyway, very simple. Take your fingers, curl them in the direction it's rotating. Your thumb points in the direction of the vector. So if this thing's going counterclockwise, the direction of angular acceleration, out of the board. There you go. Why is it out of the board? Because it's a straight line that using this rule that someone made up, it works. I can tell you which way of the angular acceleration out of the board. You can do the right-hand rule, and you can figure out which way it's spinning versus counterclockwise or clockwise. Okay? So, we have to describe vectors in terms of a coordinate system, and there is no such thing as, like, what the heck does counterclockwise look like in a coordinate system? Like, you can't draw a counterclockwise vector. What the heck does a counterclockwise vector look like? Like, it's crazy. So, which way does it point? If something's going clockwise, and this is going to be really hard to draw, it points like out of the board. If it's going clockwise, it points into the board. And the way you figure that out is just turn your hand and point your thumb. So, foreshadowing, we're going to see that with torque. That's the same type. Whenever we're describing the direction of rotational variables, right-hand rule is going to be our bread and butter. Okay? Okay.
Do you have another example?
Yeah. All right. Let's go the other way.
I just realized you're not supposed to use your left hand, but now it works.
Yeah. All right. Figured. All right. Let's just make this a question. This is a great opportunity for me to just include a slide on this. What's the direction of angular acceleration if viewed from above an object is going
There it is.
angular velocity? You got to have a reference point. Ooh, my computer is very angry. I don't know. It's just chugging right now. What are you doing, computer? All right. It's probably genuinely because people are right-handed.
It comes from how we draw the coordinate axes.
Okay.
Because it comes from the cross product of x and y. So if this
Oh,
adds up as y,
okay.
it's easiest to come out.
All right. Now I'm going to move this thing, actually.
Some people do this. I get this for like
So
magnetic
this
field
works
curling
for-
around
yeah.
a wire, but I think this is easier to see the axis. When you have
All right. There you go.
The problem.
What's the direction of angular velocity if viewed from above an object is going clockwise? Draw a picture. Draw something going clockwise. Use your right hand. Turn your fingers in the direction of clockwise, and your thumb tells you the direction. Make certain your fingers are going clockwise. That's really the only mistake There's two mistakes you can make. If you use your left hand, you're doing it wrong. If your fingers are going counterclockwise, you're doing it wrong. That's the two mistakes you'll make.
I do left hand roll every time I pull.
Oh, yeah.
Which way is your
I know.
Clockwise or counterclockwise?
My astronomy professor is left-handed, so he says, left and I love it.
Your fingers are currently going. Yes. So which way?
Yeah, I remember we were in a quiz.
Right now, your fingers are going counterclockwise. You need your fingers to go in the direction of the clock goes. There you go. Yeah. Yep. And one day, people won't know about analog clocks, and they'll be very confused about clockwise and counterclockwise, and you'll say, "Back in my day." And that'll be you. Sure.
So if we're going.
So right hand.
Like this, like
Yep.
and we're looking at
Yeah. So looking at.
so our x.
So we're looking at it from above. So we're looking at something going like this.
Right. So so or
Is your thumb going into or out?
Whatever way your fingers
you know what?
Yeah. Because all year round it's doing this.
The board, like,
As far as I'm concerned,
like
this way or that, in terms of
this is your board.
all year round, this is
And you're, yeah.
just like
goes like this, and the point is going out.
So how do you do clockwise? Yes, your yes, and you're the board. No, you're not the board.
All right. 5 more seconds. 4, 3, 2, 1. All right. So we draw a picture. There it is. I didn't say what the object is. There's the object. It's going clockwise. So really, again, this is the first thing. Do you know the direction of clockwise? It sounds stupid, but like that is the mistake. If you make a mistake, you will accidentally put clockwise as counterclockwise. How do you avoid making this mistake? Draw a picture. Draw a picture. If you draw a picture, you then have a template to follow. Your brain picks up visual information better. If you try to hold this in your head, you might start doing this, and that's counterclockwise. Okay, that's clockwise to you. It's counterclockwise to me. Great. Turn your fingers. Your thumb points. And I'm going to show you all some notation that you're going to see in the future. In Physics 2, you're going to see this notation all the time. In X. X is into the board. X is into the board. Dot is out of the board. This is a very common notation. Very easy to remember using this handy trick. You all know like an arrow, like that you shoot from a bow? Like, you know, they pull back the bow, they shoot an arrow. What's at the back of an arrow? The fletchings, the arrows. So if you all saw an arrow going into the board, you'd see the back of the arrow. What would you see at the back of the arrow? An X for the feathers. So if you all saw an arrow going into something, you'd see the back of it, and you'd see the arrows. If you saw an arrow coming out of the board, you'd see the tip of the arrow, which is the pointy bit, and it's a dot. This is a very handy way you're going to see this in Physics 2 all the time. Physics 2, you need to, like, this notation is going to come up, so I'm going to teach you it now versus then.
So, if you're viewing the object from above, isn't into the board the same thing as down?
Yeah, I mean, so in this case,
Like if it's like flat.
If it's flat on it, yeah, into the table would have been a better way. Into the ground, into the surface.
Because I did tell a few people that like.
Yeah, I look, I will put the right answer as down and into it, but and this is where I have to be careful on the test. If I gave you this on the test, I would say an object is going clockwise viewed in like you're looking at it from above. I probably would just give you the picture. Let's be real. Like these problems there's so many ways to misinterpret it. But generally, almost always, you're looking down on the object. You're always kind of looking down on it because trying to express it any other way is an absolute nightmare. So, anywho, right-hand rule, y'all. You're going to use this in Physics 2 as well. Physics 2, you get 3 right-hand rules. So, look forward to that. Yeah. Oh, no, don't worry. You do have to generally use multiple rules in a row, but, that's a future problem. Don't worry about it. You'll get to it when you get to it. All right. Yeah. We did it. All right. Great. What is the equation for angular acceleration if the angular position is given by 4t cubed? I think we're making some good progress. So yeah, we should be able to start solving some angular kinematics problems soon. And then I should be able to teach the general expression for torque. Which means next class we start teaching angular moment of inertia. And then the class after that, I should be able to connect it to torque. And if I'm lucky, teach them the energy stored in a rotating object. If I can get all that up.
We had like a week and a half complete a race with the hurricane.
Yeah. Yeah.
We had a lot.
No,
Okay,
generally.
apparently there's scope for another one.
Yeah, there's scope for another one right now in the Yucatan.
Yeah, that's wild. Let's go through that and then pick up a
Well,
bunch
there's
of.
like
That's what
4
Milton
different
did.
models like that are saying what can happen.
Yeah, it's
Man,
pretty early.
is the ocean still that warm?
That's the unfortunate part. Yes,
Year
it
after
is.
year, it's warmer and warmer.
I didn't know. The first 3 questions you didn't select the correct.
Oh yeah, thanks. I can go back and do that. Yeah. No, that's a good point. I might be able to do it. I always forget to do that. All right, give y'all like 20 more seconds. How do we go? Let me go from position to acceleration. You take the derivative of position.
There. Why is that a problem?
Alright. 5 more seconds. 5, 4, 3, 2, 1. Man, look how few. We only have 55 people today. Post test. Alright, so alpha equals the second derivative of theta with respect to time. So the first derivative, you take the derivative once, you get angular velocity, that's going to be 12t squared. You take the derivative again, you get 24t. Nope. There it is. All right, so taking a derivative, how do we do? Let's see our Calc 1 skills. They are, oh, y'all can't see it. Most people, 84% of people got it right. All right, cool. Oh, this is so funny. Ooh, I like this a lot. Okay. Ooh, my answer here is ooh, this is unpleasant. This problem is not quite kosher. Angular acceleration. Okay. Okay. When it says what is the direction of net acceleration? Net linear acceleration. This is just acceleration. Notice it doesn't say net angular acceleration. This problem's kosher. It's fine. This problem, if I just say the word acceleration, I mean linear acceleration. I mean not angular. Okay? If I use the word acceleration, that does not include angular and regular. It only includes the linear acceleration. So, I could have asked you all this question on technically test 1. So this is just a reminder. I really like this problem because it reminds you of some things. But this is something I could have asked you all on test 1. What is the direction of the net acceleration for an object spinning in a circle? And this thing is spinning faster and faster.
The inward acceleration is 1 meter per square second.
Thank you.
Yeah. There it is. 1 meter per second. Oh look, it picked it up on the thing. You're forever immortalized.
But it's on the right.
Oh, wait.
It is spinning faster and faster.
In this moment, we have obviously the triple and we also have acceleration.
The key to this is what accelerations are it what accelerations is it experiencing? Notice I said what accelerations. Sons. There's an S at the end of the word acceleration. That's my hint to you all. If you only accounted for one acceleration, if I asked you for net acceleration, that means add up the accelerations. I'm not going to have you add up things if there's only one thing.
Why is it on burn and it's vertical like across the screen?
So you got to draw actually going Y and then add those two vectors. That is the key to this. It's very subtle, but that's on my are you? No. The angular. It's the angular. Good. Yeah.
Where it is right now is just.
That's okay. That'd be fine. If you did, because yeah, that's not a. It shows you really all the things, and they're all working. Which is really good. I mean, that's hard to see. That takes time.
You know they're gonna get
Huh? What? What acceleration? So remember, two accelerations. That's for acceleration. Linear acceleration. And this is the spot. And we need Okay. So that's more so thinking about which way it's going to go. Think about the acceleration. So which way is it speeding up? That's kind of the mindset. No. Not necessarily which way it's going to whip off. Because actually, if you go at that point, not actually go. But no, but also your intuition works for one of them kind of sort of. Yeah, so try to figure out what acceleration is. Alright, I'm gonna give y'all 10 more seconds to deliberate. Alright, and 5, 4, 3, 2, 1. Alright, so there is two accelerations acting on it. There is a tangential acceleration. So let's draw that one. Tangential acceleration means, remember, this thing is moving and it's spinning faster and faster. So it has an angular acceleration, therefore it has a tangential acceleration. It has both. Okay, so I'm going to put this here. It has a velocity down this way. Fantastic. That velocity is getting faster. Tangentially, it's getting faster. Which way is it getting faster? If it is spinning faster and faster, it has a tangential acceleration also pointed down. It is getting faster in that direction at that exact spot. I had to give you a spot. What's the other type of acceleration present in the system? Centripetal. Which way is that pointed? So this one, centripetal, it's in the word center. So I've got an acceleration to the left. I've got an acceleration down. And this is where you all need to remember how to add vectors. Tip the tail. You draw one vector, you draw the other vector, and then the vectors added together. There they are. Do not forget how to add vectors. That is an invaluable skill that will serve you. Very likely in future class, definitely in physics too. Learning how to add vectors visually is a very, very useful skill. Very simple thing to do, but it gets forgotten. Down and to the left. All right. So, great. There's a picture showing it. Woo! So, same thing. This object just looks like a peanut, but it's the same idea. All right. So, great. There's that. Okay. So, this first term I already taught you all. This, that tangential acceleration is r times alpha. Remember, you just multiply everything by r and life is good. The next term is, how do you go from centripetal acceleration to angular? So here's the relationship. So AC equals v squared over r. Well, what does v equal? Remember, v equals r times omega. Remember, you just multiply by r to get from the rotational one. So just chuck that in here. So you get r omega squared over r equals r squared omega squared over r. This r goes away, that r goes away. That's where that relationship comes from. So if you want to solve for centripetal acceleration, you just multiply r times its angular velocity squared. And the derivation is just using the relationships of multiplying everything by r. Nice and straightforward, but it's handy. If you know the angular velocity, it's a nice, easy way to do it. And then, reminder, y'all, both accelerations are acting on the system. There is problems in the problem set where I say, what is the net acceleration? And you actually calculate it. And it's very straight. You just use these two terms. And the last thing I'll remind you all, actually, is it on the... Oh, yeah, it's on the next slide. If I have two vectors that are perpendicular to each other, how do I add them together? If I have an x component and a y component, how do I combine those?
Square root of the squares.
Ta-da. Reminder to you all, if you have two vectors that are perpendicular to each other, how do you add them? It's a right triangle. One side squared plus the other side squared equals the hypotenuse squared. We love Pythagorean's theorem. We love right triangles. Big fans. 10 out of 10. And in the bottom, I just chucked the terms in and simplified it. You will not see the bottom equation on the formula sheet because, again, it's a derived expression. You can do it yourself if you need it. I highly recommend not just memorizing that bottom equation because you'll use it and be like, you won't know where it came from, and then that tends to be less useful, and you'll forget it in the future. That's at least how my brain works. I don't have a good memory. I'm not going to try to memorize those bottom things. I'll memorize the simpler ones.
Or omega
Did I lose an R? I lost an R. Oh, no.
I think you switched the exponents.
Oh, I did. This is terrible. That's what it gets. All right, there's a typo here. That one should be to the 4. And that one should still have an R. Oh, it didn't work the way I wanted to. Now you get to see the joy of equations. Ooh, will it work? Oh, it did. Oh, you don't see it. Behold, there was never a problem. My lecture class will never know that I made a mistake. Yeah. Oh my gosh. Now you know there's mistakes. They'll never know. Yeah. There you go. Now it's correct. But again, that's, I'm not going to give that equation on the formula sheet anyway. I don't recommend memorizing it. Just build it yourself. Like, that sounds like a lot of work. But when you build an equation yourself, that thing on the bottom is not like a super simple r times the square root of alpha squared plus omega to the 4. Like, I don't know. For me personally, the classic. For me personally, I hated that when that was a fad in high school. When that was a phrase everyone said. It's easier for me to remember the top terms. It's easier for me to remember to go from angular to regular. You just multiply by r. That's super easy to remember in my mind. And then you can go from there. So, you do you. Okay, this is really funny because sometimes I forget about future slides. So remember I taught you all about the direction of angular velocity. And I was like, oh, let's do it sooner than later. Turns out I had a question later on about it and I just forgotten about it. So here you go. Let's see if you remember. A piece of gum is stuck to a tire that's spinning faster and faster. If the wheel is spinning clockwise and the piece of gum is on the right side, what is the direction of the angular velocity? This is just seeing, do you remember how to do this? It's been, what, 20 minutes? You might have forgotten, that's fine. This is how you learn things. You test, you wait a bit, you test again. Yeah. Make certain your hands going the right way. Look, I provided a picture, so there should be no mistakes here. Make certain your fingers line up with the way it's going. Do your fingers line up in the direction that arrow is spinning? If so, you're good to go. If not, you're doing it wrong. If you use your left hand, wrong. Look, if you haven't realized this, if you use your left hand, your hands, like your thumbs point in opposite directions. It's a weird thing, your hands, they do different things. It's called the right hand rule. If you use the left hand, it does not work. You can totally use the other side of the hand and say it's opposite the direction your thumb goes. That's an extra step. You're welcome to do that, and in fact, when you all get physics too, you'll find that electrons do the opposite things of protons. So you can use your left hand for electrons and your right hand for protons. Yeah. All right. 20 more seconds, and we'll take a break. In 5, 4, 3, 2, 1. All right, you point your fingers in the direction and your thumb points in. Like there's not too much to say there. Into the page. There you go. Into the page. Now, if I asked you this question and the wheel was spinning slower and slower, same exact problem. The wheel's spinning this way, but it's, you know what? We'll do this one before. We'll do one last one before the break. I really want to check this for y'all. It's worth the time. There is no escape. Okay. A piece of gum is stuck to a wheel that is spinning slower and slower. All right. There you go. Same problem. Two changes. I want to point this out to you. Do not miss these. If you miss these, you'll get it wrong. It is spinning slower and slower. What is the direction of the angular acceleration? The wheel is still spinning clockwise. What is the direction of the angular acceleration? And we'll go around. I'm going to chat with you all individually about this one. Okay. Which vector takes longer? What was the one that was in the phrase previously? What was that called? Angular velocity. For the angular velocity to get smaller, is my angular acceleration going the same way or the other way? Remember, if velocity is that way, it's getting smaller, which way do you know acceleration is? Me too. Even though I don't need it, I'll probably do autocorrect.
He's okay. His grade for his like regular kid. My velocity is actually smaller. It's not just using right. You have one thing.
Alright. Make certain I'm circling around. Which way is Good. Okay. Did someone check with you all? What did you all put? Okay. Doesn't mean you're wrong. I always ask. Opposite of what? Opposite of, because what vector was pointed into the page? The angular velocity. So yes, it's opposite. All right, great. I think we have checked around with everyone. It looks like all their answers are pretty good. For there is some subset that aren't. But we'll close this out in 5, 4, 3, 2, 1. So the key here is realizing that you already know that omega is into the page. So remember, acceleration is always based upon how is my velocity changing. So is my angular velocity getting bigger or smaller? The magnitude of it. Smaller. How do I make omega get smaller? I make one that's out of the page to cancel it out. So, remember, acceleration is all based upon how my velocity is changing. A positive acceleration does not mean you're moving to the right. A negative acceleration does not mean you're moving to the left. A positive acceleration means your velocity, the magnitude, is getting bigger. A negative acceleration means your velocity is getting smaller. So, that's just something I want to remind you all of. All right, take a break, rest your brains. You got like 5-7 minutes. Go to the bathroom, do what you need to do. Next, we'll practice some kinematics. Angular kinematics.
What day are we going to the lab?
Tuesday.
Gotcha.
Yep. We have a lab Tuesday. It's a good reminder. Lab Tuesday. Same as always. Yeah, same as the new always.
Hello, Professor.
What's up?
Sorry to be late. I sent you a message about it, though.
Okay. I have not checked any messages, but
I was stuck in the highway, so I was late.
Okay. Okay. I mean, it's so 4 absences already. It's like 4 days worth of absences already. Those are probably just all Where's your car? Oh, you're on the side of the highway.
Yeah.
Oh, okay. I thought it was traffic. Yes.
No.
Yeah, I'll see that.
A tarp, and it got stuck in the drivetrain, and that's why I sent you a video about it.
Why did you get it? Oh goodness. Angelina, would you mind marking him as? Yeah. That's fair. Car troubles, those ones count as excuse. I thought it was like car traffic. No. Well, some car traffic.
Thank you, sir. Here? Thank you.
Oh,
yeah, no, I clicked and see the whole bottom of my screen is acting up.
It won't change. Yeah.
The whole phone charger core is like messed up,
It's
and then
pretty
that
scary.
messed up.
You can shoot me an email if you want, and I can give you the points. That's something I have to do kind of after the fact. It's only 0.25 points for a single question, so it really won't change much. But shoot me an email.
Yeah.
Shoot me an email, and I can.
Thank you. So, I was driving with a tarp, and then.
Oh, nice! You like.
Yeah, this is a video I sent my family for. So I was on the left side, and I really hate the left side.
Yeah, it's really dangerous.
So that's what got stuck in the side of my car, and I couldn't drive forward.
So how did that? You're just driving. You ran over a tarp.
Yeah.
presumably.
Well, it was a truck like.
Oh, you're
3
fine.
cars
Yeah,
in
yeah,
front
yeah,
of
yeah.
me.
It fell off, and like I'm
it
not,
fell off,
not as
and
a blame game thing.
Everyone like braked, and I braked as well, and I like tried to avoid it, but once I went to the left, the thing went to the left with me, and I ran it over.
And then what? Your car just like slowly slowed down, or did
Yeah,
you?
they basically like locked up the rear.
That's really bad. So your tires just skid?
Yeah, pretty much, kind of.
Oh, that's really dangerous.
Yeah, so that's why I had to go to the left real quick.
Did you have a knife on you or something to cut
I
it up?
did not. I had a scissor on. I had like
Oh, you
like,
had scissors,
like
that's
kid
good.
scissors on
At
me.
least you had that.
So I was on
Yeah.
the side of the highway, and then I called like road assistance, and I called my brother, and then there was like
You just looked
construction
under.
people.
Yeah.
There was like construction people, so I like went up to them. We were like, "Oh, can I have a knife? There's something stuck under my car," and then they didn't have a knife. And then I know that's so like exactly. And then I just had to wait for my brother to get there with a knife.
Okay. Oh,
And then
sorry. This is all on the stream right now. So.
Yeah, I'll watch it later.
No.
Oh.
No, I meant everyone's hearing your story.
Great,
Yeah,
such a great
I
story.
I haven't quite.
Now it's in the internet forever.
Yeah.
It's great.
I've tried to figure out. There's a way to do it.
But yeah, that's what happened. So sorry to be late.
At least you and other people are all not injured.
Thank you. Yeah. Yeah. I agree. Okay.
Oh, there it is.
You get to chill.
Now,
Yeah.
am I getting any emails? Hey, the good news is my captions were working, so you know.
You win some free.
Yeah, the accessibility wins out.
That's what I like. I only want those 2 pieces of information. I don't remember what it was asking.
How many seconds did it accelerate to 3 revolutions per second? How many seconds did it accelerate?
5.
5.
All right, the blinky blinky will be up there for a few more seconds. If you need Leo, Leo's got you.
I am here.
Remember to ask. She needs you.
Oh. You're obstructed by that.
Yeah, you're invisible. All right, back to the question. The key to this is, can you figure out the givens? So I'll show you what those are in like a minute. If you can figure out the givens, you can probably piece it together from that. 3 revolutions per second is not the angular velocity. That is my major hint to you. 3 revolutions per second is not angular velocity. You have to do something to it. So revolutions per second, that's not it.
These markers stink. Is that like?
Oh, like actually stink?
Yeah. No, like they like with the smell. Is that right? Like, I'm like so today. Just multiply that by 2.
That's the 3 rep second is frequency. So define. It's not actually.
Well, it's gonna if I yeah.
I named that 14.
Yeah.
Me as well.
Thanks. Is it 14?
That was actually yesterday.
Yeah, what's the best rate? Three times two. We're dead inside. That's also, and that's only you. I mean, probably. Oh, you didn't. That's how you're gonna make sure you do it correctly. We know the equations work. You can kind of build an equation, but it's hard to kind of validate that. All right, so let's write down our givens, y'all. R is 0.3 meters. Like, look, I'm going to just trust that you recognize that the radius R is 0.3. Okay. What other variables? You all tell me. Okay, look, time is 5 seconds. I'm not going to, I assume you all know that. What else is given in this second? Actually, time is not, okay. It is and it isn't. The time both is 5 seconds, but you're going to use a different time later on. I'm not sure how to label that so you understand that, but we'll talk about it when we get to it. Okay, what else is given? The initial, we do have the initial velocity. Angular or regular? Angular. Sure, let's do angular. We can do both. Yeah, let's just, clearly it doesn't want me to erase this. So we're going to leave that. I have no idea why this does this. Ooh, it worked. Initial. If I just keep doing it enough, it eventually accepts my efforts. And it's gone. Whatever. You'll just be confused. I'll fix that later. All right. Omega. What else is given? There's another number given in this problem that we haven't worked with yet. We'll eventually use that. I'm not going to touch that one yet. But yes, that is one. 3 revolutions per second. What variable does that go with? There is technically a variable it goes with that I both have and have not taught you all. Like I've mentioned it in this class at some point. It is frequency. So if you've taken physics before, you might know that this is frequency. It's okay if you don't. It's okay. Like, again, if I haven't taught it to you, I'm not expecting you to know that. This is frequency. What is frequency? It's how many times something happens in 1 second. That is what the definition is. It's how frequent something is. A full cycle. Here's the problem. Is frequency in any equation I've given you? No. What is in the equation? What would be handy? And we'll call this frequency final. How can I convert that to omega final? What's the units for omega final? What's the units for angular velocity final? Or no, what's the units for angular velocity?
S to the negative 1.
It is s to the negative 1. And what's kind of on top of it? That secret unit? Radians. How do I go from a revolution per second to a radian per second? Yeah, how many radians are in 1 revolution? Look, you all just derived this expression. That is an equation, and I think it is actually on the formula sheet, but you all just derived it. How do you go from revolutions to radians? Just multiply it by 2 pi. So omega final is just 3 revolutions per second. I'll actually put the units here so you can see what's going on. Times 2 radians per revolution, 2 pi radians per revolution. The revolutions cancel, and you get radians per second. All right, y'all go. Now, step 2. Okay, I'll do this last step with you, and then I'm going to let you finish it up. What are we solving for? We are solving for net acceleration when? At 0.5 seconds. And you can decide whether or not it matters that it's at 0.5 seconds. So try it out, y'all. Try it out. Think about it. I want your brains to process through this because you can do it. You all can solve this problem. There is so many ways to solve this problem. I say so many ways. There's like 2 or 3 ways. You can work in linear variables. You can work in angular variables. Pick your poison. I'll do both. So what variable are you solving for? And remember,
True.
This is 2 different shares. Always. The acceleration. Yeah, the centripetal one is. Oh, and I'll put the answer up here. I don't know what it is off the top of my head. Yeah, it likes to put it over here. Boop. There's the answer. This problem's got some complexity to it. There we are. All right, question for y'all. Why did I put A net? Why didn't I just put A? It's looking for the magnitude, and what does the word net mean? Total, which means there's more than one. What are the 2 accelerations that are occurring? The 2 tangential the 2 linear accelerations, what are they? Tangential and centripetal. How do I get those? How do I get them together? So A net equals the square roots of AT squared plus AC squared. If you have 2 accelerations that are perpendicular to each other, remember this is a throwback. This is number 8 in the problem set. This is not a simple problem. That if you're like looking at this like, oh my gosh, this is so difficult. Yeah, I jumped to kind of a tricky one. But what's cool is you all can do this. Like I jumped to a more complex one on purpose. You can do this. You all have all the skills, you have all the equations and know how to do this. Put the puzzle pieces together. And I'm here to help you. Just start writing things out. How do you find the tangential acceleration? How do I find the centripetal acceleration? Just start Working the problem is what they call this. When you're stumped, just start working the problem and see what you can do.
I think it would be 1/5. Yeah. As a function of time, I just divided it by 5.
Yes.
And this is a function of time.
Yeah.
So
Radius.
yeah, this is the AFT at 0.5. For AC triple, so I want to get this. I need to find the tangential for that. So I want A at 0.5 is
They always say that.
Why are you dividing with
I don't know.
Since 6/5 pi, if I just plugged in a time, it wouldn't. I'm trying to make it acceleration as a function of time.
Yeah, that's a really common.
So I can plug in AT to get an acceleration function. So this is I'm finding this at 0.5.
Yeah, that makes sense.
And that'll give me something. I'll just denote it A 2.5. And then
You already did that like when you found your radius, right?
No, they're all simple.
I know it's
Oh, okay, there we go. There we go.
so you could do like omega 9.5 seconds.
yes.
And then
So
yeah, that would be great.
if I have the acceleration, can I try to make that perfect?
You just have the
Oh, no.
general angular.
Yeah, I just
acceleration.
need
It
general.
doesn't need to be at
Because omega at t is what if you want to have.
Yeah, it's the same idea as like
Pi over 5.
So just 0.5 squared.
Is it 1/2?
Average.
So I think this is at t. So at the t that we're looking for is 0.5. And then AC is going to be 0.5 squared times r. And the magnitude of the total acceleration.
You guys are so smart that you guys are working it out. And you will learn.
Okay, so
I think I understand this.
Yeah.
But I don't understand this.
The tangential?
Yeah.
Okay. You asked fantastic questions. Do you have the slide pulled up?
Yeah.
It'll make more sense. Are you plugging it? He's gonna plug it in.
So in the problem set, sorry, I'm not running away from you. I'm putting all the pieces because I think it makes it easier to check your work. All right, there's all the things. Not very useful, is it? All right. How much is this going to break things at this point? Okay. So, the key to this problem is, again, every physics problem, break it into smaller pieces. So actually in the answer, I'll give you all the answer in terms of like all the pieces. So if you all work in this one later on, you can kind of check individual pieces. Work the problem. Work the problem. Now, something to note here. Is my acceleration changing with time? Have we ever done a problem where acceleration changes with time? No, I don't know. Like every single problem I've basically ever given you all, acceleration is a constant. We're going to assume that in this problem. Acceleration is a constant. So we just need to break. Okay, so look, we know we're going to find the net acceleration. Pick a piece. What do you all want to do first? Tangential acceleration or centripetal acceleration? Tangential it is. There is many ways to do this. Many ways to do this. One, you can do it with kinematics. You can use any of these kinematics equations here on the left. You can do this one. Velocity final equals velocity initial plus a times t. And then the question is, what is v final and what's v initial? We can find that. So there is so many ways to solve this. What's v final? It's just r times omega. Now, okay, this does get a little funky. This might get a little tricky for us to do because we have to find omega at 0.5 seconds. And that's a little, like, that requires an extra step. So we're probably not going to want to do that. We don't know omega at that point. But that is one option. You know what's an easier one? A equals R times alpha. A equals R times alpha. What's alpha? What a good follow-up question. What is alpha? Someone tell me. What does that represent? Alpha is the angular acceleration. Alpha is angular acceleration. Look at your all's thing. Look at the rotational side. What equations have alpha in it? This one, and this one. Looking at those, you all tell me what's the easiest to use based on what you have. Check out that first one. Omega t equals omega initial plus alpha t. So, omega final equals omega initial plus alpha t. And I'm going to copy all this to another.
I did position.
So this problem, y'all, it's really about the relationships between the variables. And then just kind of work in the problem. So, Nero, I'm actually going to do this and make it a little bit easier. So, omega final, alpha equals omega final minus omega initial divided by time. Equals, what's my final omega? 6 pi. What's my initial omega? 0. What's my time? So, boom, that's my alpha. Alpha is just change in omega over time. And then A just equals R times that. 0.3 times 6/5 pi. Which is going to be 1.8 divided by 5, and that's not a nice number, so I need a calculator.
You got one?
Oh,
thanks. You already got one.
All right, so you get A equals 1.13 meters per second squared. Yay! One variable done. That's not the final answer. Now, let's look at centripetal acceleration. What's the equation for centripetal acceleration? It is r omega squared. What's the one that you all remember? Let's kind of remind ourselves how to get there. Vt squared over r. Now, you have many options for how to figure this out. You all have A at this point. So there's many options. There's one option that was mentioned. You all can do the r omega final squared over r, which is going to end up being r omega final squared. Here's the thing, though. You got to be very, very, very careful. If you all put that omega final is 6 pi, you'll get the wrong answer. Why? When are we finding the centripetal acceleration? At 0.5 seconds. Do we know omega at 0.5 seconds? Can we find it? At 0.5 seconds. I want you all to try this. Find it. Find omega final at 0.5 seconds. Try it out for yourself. Given what I just did, all the nonsense I just did, see if you can figure it out. Oh, like the actual right answer? Oh, sorry. The actual right answer is 1.065. Yeah, this is I've chosen this problem because this is a fantastic one for y'all to practice to make certain you understand angular and linear variables. This problem has it all, which means it's complex.
Alpha?
That only works. What's the angular acceleration? Yeah. Hey, you got acceleration. You got time. How do you find final velocity? All right, so how do you find this? How do I find angular velocity? So here's the problem. Someone raised a really good point. They're like, hey, can we just divide 2 pi by the time? Unfortunately, we can't. Why can't we? Why can't we just divide the angle by the time and say, yep, that's the velocity? What is this thing doing that prevents us from? It's accelerating. It's accelerating. So, question is, how do I find final velocity if I have the acceleration? It's the same equation that we just used. How do you find final velocity equals initial velocity plus acceleration times time? We just found the angular acceleration, y'all. We have it. So this equals 0 plus, there's my acceleration, times 0.5. So you get 3/5 pi, and that's a number. I'll plug it in. 1.88. All right. So great, you all got that. You chuck it in there, you get the acceleration, and that's kind of straightforward. That's one way. You can now plug that in. So this is one way of doing it. Remember, there's so many ways. You can do this problem in linear or in rotational. What's the other way? What if we instead just found the tangential velocity at that point? How do I find the tangential velocity at that point? VF equals V naught plus AT. What's my initial velocity? What's my acceleration? You all just found it. So you can also do it this way. You can also do it using linear acceleration. Again, I really, really, really like this problem because it really lets you kind of mess with the variables and play around and see kind of the relationships between them. I highly recommend you all work up this is one of those that if you can't do this problem by test 3, it doesn't mean that you don't understand. Let me rephrase this. If you can do this problem without looking at the solution by test 3, it means you understand these variables pretty well and the relationships between them. That's the way I'm going to phrase this. So that's why this problem's so useful. So anywho, you plug all these things in. What color am I going to pick? Blue. So long story short, many, many ways to get this. What's my radius? 0.3.
I solved it, yeah. That's why I took a double. Or double interval, I guess.
All right, last step, y'all. Just add the square of those, and you get the right answer. All right. Okay. So again, lots of things going on here. Lots and lots of things. I mean, again, this is number 8. This is not a simple problem. It's not number 1 or number 2 or number 3. So if you're like, man, this is really complicated, I have no idea what's going on, do the problem set problems where you start at number 1, it's number 2, number 3, and you build towards this. I'm jumping to this one because the problems I want to show you all in class are ones that show you kind of all the things. This problem shows you all the things. It shows you the relationship between alpha and A. It shows you the relationship between omega and B. So if you're like, why did he pick such a complex problem? It's because I only get to solve 1 or 2 problems with you all. So I pick ones that show you all the things. I don't expect you to fully understand this problem right now. If you fully understand this problem right now, that means you understand everything I just taught in the last 2 hours, which means great. You actually don't need to do too much more practice on it. I don't expect that. I expect that maybe for 20% of you to fully understand everything. The vast majority of you all, I expect this to be a problem where you kind of practice, it hurts your brain a bit, and in the future you work on it yourself and it starts to make more sense. Okay? So that's the mindset. All right, there is one last thing I do need to cover today. Because again, we got to cram stuff in. One last thing, and it's torque. I can start to teach you all torque, and the good news is torque resets. Torque's it resets in the sense of the complexity resets. We're not starting from this level of complexity. Okay, so torque. Let's see, is it in this problem? All right, see, case in point. We're going to reset complexity. Oh, and I apologize. There is a second right-hand rule. Y'all get 2 right-hand rules in this class. Oh, gosh. I do the swinging one. I like the swinging one better.
I do both.
Yeah. All right. If I have a bolt and a nut that's stuck, should use a long wrench, a short wrench, or it doesn't matter. If you have a bolt's a thing that screws onto a screw. So it's a metal thing that screws onto it and it's stuck. Yeah. If you have something that's stuck, do you use something that's... If you don't know, just guess. The other example I give to you, when you want to open a door, do you push close to the hinge or far from the hinge? Open the door. I guess you can say close the door as well. Close or open. All right, 15 more seconds. In 5, 4, 3, 2, 1. So again, this is something, the whole point of this, there is a ton of examples I could have given you all. Which, you all got this right. Which one do you use? Along, Rich. Another version of this problem. If I want to open the door, where do I push the door? Close to the hinge or far from the hinge? Far from the hinge. If I want to use a crowbar and I want to pry something up, do I hold it close to the fulcrum or far from the fulcrum? Far. Long story short, what variable are you changing when you're getting farther from the pivot point? It's the radius. As R goes up, is your force, do you have to push hard? If you're pushing with the same force either way. But to get the same effect, so here's the equation. Here's torque. Torque says R cross F equals torque. And we're going to learn what that torque is. But for now, know that torque is just kind of like a measure of the force. It's like force, but rotation. A torque makes something accelerate, angular. A torque makes an angular acceleration. A torque makes an angular acceleration. A force makes a linear acceleration. A torque makes an angular acceleration. That's the connection here, y'all. A force makes a rotation, a tangential acceleration. A torque makes an angular acceleration. We're going to see that there's a Newton's second law for torque. We'll learn it eventually. The units for torque literally come from the math. What's the unit for R? Meters. What's the unit for force? Newtons. What's the unit for torque? Newtons times meters. Ta-da! That's the units. They're the same thing. And there is a cross product. That X is not it is a multiplication sign, but it's a very special multiplication sign. Yeah, this is Calc 3. Torque, yeah, so cross product. And I'm going to hopefully explain what a cross product is to you all, and hopefully it'll make sense. It is RF sine theta. I'm going to remind you all of the dot product in a second, but I'll wait. Yeah, there's a few things I got to teach you all here, and this is kind of the last thing.
Because honestly, the cross product is like the only thing I can do right in calculus right now, because then it's like if you search the cross product, and then just what we're as long as we're not there.
All right. Can someone remind me? Remember, work was the integral of f dot d. That's a dot product. What does the dot product turn into? Times cosine of theta. A dot product is a cosine. A cross product is a sine. You are still multiplying vectors, but in one case, you multiply them and chuck a cosine. In one case, you multiply them and put a sine. And remember, the dot product, if this is the direction it's moving, and this is my force, and I draw a triangle, the cosine, does it give me the part that's parallel to D or perpendicular to D? If y'all look at this picture, and I find the component of F using cosine, does that give me the perpendicular part or the parallel part? It gives me this part. So, check out my picture here. if I multiply f times the sine of the angle, what's that going to give me? The perpendicular or the parallel? The perpendicular part. F times, why am I writing that in an angle? F times sine of theta. Very, very obvious if you make sense of it. Y'all, if I pull this thing, does it spin? If I pull this meter stick, is it spinning at all? No. If I pull away from it, it doesn't spin. If I push towards it, does it spin? No. Which way do I need to push this thing to spin it the most? Exactly perpendicular to the arm. A cross product literally just said, this torque, this cross product just says, you only spin if I push perpendicular to it. You find the part that's perpendicular to it, and that's what makes it spin. That's what it's doing. That is what a cross product is doing, is finding the part that's perpendicular to it. The parallel part does jack squat. So you find the part of the force that's actually perpendicular to the arm. That's what it's doing, okay? I hope that makes some sense, because cross products, it took me forever to understand that. No one told me that, ever. They just kept showing me how to do a cross product. But dot product, parallel parts. Cross product, perpendicular parts. That's literally all they're doing. They're multiplying vectors in those two ways. Yep. For torque, we're going to use the sine because we're going to find the part that's perpendicular to it. So there you go. New right-hand rule, y'all. Here's how the new right-hand rule is going to work. Point your fingers in the direction of R. Which way does R point? From the center to wherever your spot is. So let's look at this picture here. So R points up and to the right. And unfortunately, my screens are all in different spots, so I can't be consistent. Up to the right. And then imagine that you swing the R towards F. And your thumb points in the direction of the torque. So let me show you all on this screen. I take my flat hand and I point it in the direction of R. Great. Is it possible for me to swing my fingers towards F right now? The way my hands, I can't. So what do? I turn my hand so that I can actually swing R towards F. That's kind of the logic I use. I almost think of it like a door swinging towards us. Make your hand so that you can swing R towards F, kind of like closing a door. So, look, if I have my hand this way, can I swing my fingers towards F? No, it's not happening. So you just turn your hand, and your thumb points in the direction of torque. So, make it so R can swing this way, so I can go woo, and my thumb points in the direction of torque. If my force was the other side, I would swing it this way, and the torque is that way. Fun fact, what is your thumb pointing in the direction of? The way it's going to accelerate. The angular acceleration. The torque points in the direction of angular acceleration. That's what you're finding. That's the purpose of this. All right? So don't worry, I'm going to practice it a bunch because it's a pain. There it is. Look at that. Look at that nice slide. Make your hand flat and point in the direction of R. Rotate your hand, rotate it like you're giving a princess wave. So that you can make it so that it can point in the direction. And look, here's 3 practice problems. Try them out. Try out the first one. Find the direction of torque. We're going to do each one together. So we got number 1, number 2, and number 3. And each problem, I give you less and less information. Number 1, point your fingers in the direction of R. Turn your hand so it can... Ooh, that's so... Sorry.
When I walk under the microphone, it doubles it.
Oh, that way.
Yeah. So you point your fingers in the direction of R. Rotate your hand so it can point in the direction, so it can swing it towards F. If you want, kind of think that point your palm in the direction of F. If that's easier, point your palm in the direction of F, and woo, thumb points out. So first one, thumb points out. Because we're going to swing it this way. When you know which way to swing it, you can kind of think of that whole thing we were doing before. All right, so which way do I swing it? I swing it that way, and I get a out of page. You all try the next one. Which way do I need to make it so I can swing R towards F? Remember, your fingers have to point in the direction of R. Your fingers have to point in the direction of R. So I'll give you all a few seconds to try that. If you point your fingers towards the inside of the circle, you're doing it wrong. This is wrong. Do not point your fingers this way. Your fingers have to point this way in the direction of R. And I need to swing that R down to F.
So you point your finger in the direction of R.
Yep, because your fingers aren't pointing in the direction of R. They're pointing in the opposite direction. Yep. And if you're like, man, how do I swing it? Through the magic of moving a vector, that's the same thing. If you're like, how do I swing it? Just make it bigger. So I move my R, I make it kind of longer to make it more obvious. And which way am I going to swing it? I'm going to swing it that way, clockwise. Which way does your thumb point? Into the board, into the page, into the board, however you want to put it. All right, great. So we see that one. The last one, you draw R. The last one, I didn't draw R. You do it. You have to draw what R is. Draw the R vector. You can do it. I believe in you. Start in the middle. Draw to the spot you care about. Yep, because which way is R pointing? If you had to draw the R vector, which way would it be? So you want to draw from the center to the point of interest. Where the point is. So can you draw R? How do you draw R? You start in the middle and you draw R to the point of interest. Where's the point of interest? Where the force is acting. R. So there's your R vector. So again, make it bigger to make it easier to see. Which way am I going to swing it? Clockwise. You all, this is an important skill because if you cannot do this, you cannot figure out which way it's going to accelerate. If you cannot figure out which way it's going to accelerate, you don't know what's going to happen. But again, you all can look at this picture. Which way is it going to accelerate? Clockwise. You can actually use that to figure out the direction of torque. That's another easy way to do this. Yeah, so if y'all want, just figure out which way it's going to accelerate. And then use the other right-hand rule and you can figure out the direction of torque. It is this.
So what does that tell you?
It tells you how much angular acceleration you get. So the more torque you have, the quicker you can accelerate those tires. Or inversely, you could also think about it, it's like the more force you can kind of apply. So like torque, so like trucks, the Tesla truck, any electric vehicle, they have insanely high torque. What that lets them do is accelerate extremely quickly because they can angular accelerate those tires extremely quickly. It also relates to like big vehicles. Big vehicles, it also, you may be like, so like a semi truck has a ton of torque. You may be like, they don't accelerate that quick. Yeah, they're massive. Like the amount of mass they're having to move is much more. So they need that torque to, they aren't making a large expansion. Yeah, so they're fighting a lot more mass. All right, so let's see how much this makes sense. You know, I've gone around. Now I actually get to see if you actually understand it without telling you anything. All right, so I think we're good here. Just whether my lecture class, like we'll be able to actually get through this. Oh, my lecture class is a challenge. This has mostly been me just chatting. There's not much problem solving. This is concept. This is fine. I mean, it's a lot of information subject, but it's doable. Yeah, my lecture class is going to be. Again, now we're 20 minutes. It's going to be just skipping through some problems and the answer, go back and look at it. And then I will just solve through that problem, the same one I did with. Yeah, I won't give them any time to figure it out.
Wait, is he not chin?
All right, 15 more seconds. 5, 4, 3, 2, 1. All right. Let's do this both ways. Which way will this thing accelerate? Which way will the angular acceleration be? Clockwise or counterclockwise? Counterclockwise. Rotate your fingers counterclockwise. Torque's out of the board. That's one way. Let's do it the other way. R points this way. Also counterclockwise. You get out of the page. Let's see how we did. Fingers crossed. Yay! The torque is a notoriously tricky thing. The right-hand rules are always a pain to teach. They're very visual. So I'm glad to see it's going decently. All right. Okay. I want to try to solve one problem with... do I want to try to solve one problem with y'all? Maybe not. But I'm going to show it to you. I'll talk about it for like 5 seconds. We'll call it good. I want this full screen so you can fully appreciate the majesty of this guy. All right. Why do we care about torque? I've already mentioned this to you. Why do we care about torque? It results in an angular acceleration. Who's the mad lad who did a lot of things with acceleration? Yeah, there he is. Look at that guy. So, next class, we'll calculate torque, and then we'll start to do problems where we actually calculate the angular acceleration. I have to teach you all moment of inertia first. So next class, I have to teach you all moment of inertia. It's going to be a good time.
It's also a good time for you to let me know.
Moment of inertia is not pleasant to calculate. It's the one new thing. So all these other things are like really strongly connected to other things I talked about. The variables and how we interchange them. Moment of inertia is how the mass is distributed. It's how the mass is distributed away from the movement. So it's kind of like center mass, but instead of the integral of mr, it's the integral of mr squared. Yeah. That's fine. It's fine. I'm not going to give you all any crazy problems with it. No, so like we'll talk about it. I'll give you it for a bunch of objects. We can't even derive it because you need double check integrals for three-dimensional objects to derive it. Those are fine. No. They're literally just doing an integral more than once.
But like, I had to jump on the foundation of doing integrals.
Oh, okay. Well, yeah.
Like, just do Q, Jessica. Like, just find it out.